Hi, this is Dave Johnson with another edition of Math Off Topics. Today I want to evaluate a definite integral without using an antiderivative. In other words, I want to use the definition of the definite integral in terms of a Riemann sum. And it's not going to be your typical linear function or quadratic function. It's going to be a little bit more complicated. We're going to try to do the cosine as the integrand. So let's get into it. So I've taken the liberty of writing a few things down first. The integral that we want to do is the integral from a to b of cosine x dx. Now, of course, you all know how to do this because the integral of the cosine, the antiderivative, is the sine. But let's pretend we don't know the antiderivative. And to keep things a little simple for now, and we'll generalize this at the end, but let's suppose that the lower limit of the integral is 0. And so we're writing this integral in terms of the definition using the Riemann sum, limit as n goes to infinity of this sum as k goes from 1 to n of cosine of x sub k times delta x. And so I want to have a handle for this integral. I'm going to call this I. And let's suppose that and we know delta x is equal to b minus a divided by n. And in this case, a is 0, so we have b divided by n. We also know that x sub k is equal to a plus k times delta x. So since a is 0 and delta x is b over n, I can write that x sub k is equal to kb divided by n. I'm going to plug these in and take the limit. So let's write I equals limit as n goes to infinity of the summation as k goes from 1 to n. And let me just go ahead and write it as is. So cosine, so x sub k is kb over n. And then we're multiplying this all by delta x, which is b over n. Okay, so to simplify things a little bit, I'm going to bring the b over n, so that's this, bring that out of the summation. I can't bring it out of the limit. I could bring the b out, but I'm just going to leave it there for the moment. And so let me write that. So limit as n goes to infinity of b over n times the summation as k goes from 1 to n of cosine kb over n. Now, the way we're going to do this is I'm going to use the Lagrange trigonometric identity. And you can see this derivation in various places. I'm actually going to do a video that derives this identity. It's not difficult, but it's a little lengthy, and I'm not going to put it in this video. So the idea behind Lagrange's trigonometric identity is that you can write the sum of cosines with various indices as a, so this is a summation having n terms, and you can rewrite this in closed form in the following way. And that's going to be handy because when we take the limit as n goes to infinity, we'll have an infinite series here, but we'll still be able to write it as the limit of this expression. And we'll find that evaluating that limit is not very difficult. So let me go ahead and make the substitution. So in this case, the theta is our b over n, okay? And notice that k does not appear in this expression. So, but the theta does, and so we'll be replacing theta with b over n. And so let me go ahead and rewrite this. So this is equal to the limit as n goes to infinity of b divided by n times the summation. Well, I'm going to use this expression in the Lagrange identity. So times 1/2 times -1 plus sine of n plus 1/2 times theta, but theta is, as I said, b over n, and then divide by sine of 1/2 times theta, but theta again is b over n. And close bracket. Okay, now simplify things a little bit. I'm going to go ahead and bring the b over n times 1/2 inside the brackets and keep writing the limit here. So limit as n goes to infinity of, and let's just write it this way. So -1 times b over 2n, so negative b over 2n. We're going to see that that term goes away when we take the limit, plus, and then I'm going to go ahead and distribute here and simplify this. And so we get sine of, now b over n times n just gives you b plus, and then 1/2 times b over n is b over 2n, and divide by sine of b over 2n. And I forgot, I've got to put the, so this is times the b over 2n multiplying this whole expression. So let me write that here. So b over 2n. Okay, so now we want to take the limit of this. This is going to go to 0, as I said. The limit of the sum is the sum of the limits. And so that first term, the limit of that is 0, because then it's going to infinity. And so we look at this limit here. Well, you're going to have this sine of b plus b over 2n times b, but this is going to go to 0, and so you're going to get a sine b, but there's a, what about this? This looks like sine of 0. So the easy way to do this is going to be to write this as, so limit as n goes to infinity, and I'm not going to write that 0. So we get sine of b plus, I'm going to go ahead and say this goes to 0 as well. And then divide by, now I'm going to go ahead and bring this downstairs and write it as underneath the sign. So let me write this as sine of b over 2n divided by b over 2n. And you can see that this is exactly the same as what we had before. If you divide by a fraction, you multiply by the reciprocal. So this is the same. But when we take the limit of the downstairs here, well, as n goes to infinity, you get sine of 0 divided by 0, which we remember the limit of that is 1. So the limit of this denominator is going to be 1. And so I can write this now as sine b. And that is our result. Now, you might say, well, wait a minute. We wanted the integral of from a to b of cosine x dx. And all we've really got is the integral from 0 to b of cosine x dx. Well, that's going to be easy to fix. Let me go ahead and show you how to do that. So the integral from a to b of, let's say, cosine x dx, that's equal to the integral from a to 0 of cosine x dx plus the integral from 0 to b of cosine x dx. And what we have found is this integral here. This is sine of b. But let me rewrite this. So this is sine b minus, now why am I putting a minus sign here? Because if I change the order of these limits, then this is going to become the minus the integral from 0 to a of cosine x dx. And of course, this is just sine a. And so summarizing, the integral from a to b of cosine x dx is equal to sine b minus sine a, just as you would expect using an antiderivative, using the fundamental theorem of calculus. But we didn't have to know the antiderivative to do this problem. So I hope you've enjoyed this video. If you found it helpful, please like and subscribe, and I will see you in the next video.